Okay, it's 7:30 and we're going to get started. Welcome to the August meeting of the Johnson Space Center Astronomical Society. I'm Doug Holland, the president of the JSC, and here's our here's our agenda for our meeting this evening. First, we're going to have Al Mowry, who's going to be bringing us Building My Equatorial Mount Telescope. Then Kayla LaFrance will be telling us about James Webb, a photo introduction. Then I'll have a DIY astronomy on astro imaging automation and 2 members' minutes, one about our second semi-annual pizza astronomy conference, the second one about galaxy tables. Then we'll wrap it up with David Havlin with Star Party News. And then we'll wrap it up and we'll finish it by telling you what we're going to be doing next month. If you have questions or comments for our presenters, you can send your questions to jscslive@gmail.com, or you can enter them in as a YouTube comment if you have an account that will allow you to do that. So first up, we have Al Mowry with Building My Equatorial Mount Telescope. I'm going to transfer it over to Al.
Al, you have a go.
Hello, everyone. My name is Al Mowry, and my talk is about how I built and got to the telescope I have now. Several of you have seen it at the star parties, and it might seem a little odd. This is a picture of it at El Dorado. But you know, that's the nature of home-built telescopes. I started to build the telescope at the peak of my career. I only had some evenings free, and I wouldn't be able to travel very much to use it. So it started as a backyard telescope. My telescope is an equatorial. Today you'll see that most people are only building Dobsonian type telescopes because they're a lot easier and you can build them out of wood. But you know what really makes the equatorial a lot harder to do is, well, it can be very heavy. It's made out of metal. But what's good about it is it aligns itself, you align it to the pole of the Earth's rotation. And to do tracking, to keep your telescope aimed at the star you want to look at or your object, you only need to run one of the axes. So in some ways, it's a little bit simpler. And equatorial mounts are usually used in photography. Dobsonian telescopes are typically used for visual observing. So I'll go over these a little bit later, but this is where it all began for me. The first slide is 2 books. I threw them in here because I happen to have them. I started in the 1990s. Wasn't a lot of computer stuff that you could learn. In other words, you couldn't learn a lot through the internet. But on the left is an old Edmund Scientific book that talks about telescope making, eyepieces, mirror making. And then on the right is a Sky Atlas 2000, which is a very large map and has lists of objects and has the constellations and all the star fields. So you would basically use something like the Sky Atlas, look in the sky, try to find one of the constellations, start at one of the stars, and kind of move around the sky, looking through your eyepiece to make sure you were on target and trying to get to where you wanted to go. The next picture is where it really began for me. This is a modern picture. This I took just recently, but this is a 4-inch telescope. It's something like an F10. It's a very long tube, about 4 feet long. This is an aluminum tube. My dad helped us put it together when my brother and I were very young. And we ground the mirror for this. We used the Edmund Scientific book and we ground the 4-inch mirror. Our dad helped to make sure it was figured right. We sent it off for mirroring and we used it a little bit, but we never really had a good mount for it. So my experience was kind of limited in astronomy. The next picture is kind of where I went to. So on the right is an equatorial mount and on the left is a Dobsonian mount. I started off with a 12.5-inch mirror that I ordered from Taurus Optical. I really didn't know where I was going with this, but I knew the first thing was to start with the mirror. And a 12.5-inch was picked because I wanted to do some visual astronomy, but I wanted to have some capability to do some photography. And it seemed like a 12.5-inch mirror was going to work okay on a decent sized mount. So I started building the Dobsonian telescope on the left, but about that same time, I found that I could get a equatorial mount. This is a star finder. It's made by Meade. And I was able to get this lower half, not the tube assembly, but the mount itself, for a pretty cheap amount of money. It's pretty crude and rudimentary. Most of it's made out of steel and a little bit of aluminum. But so I quickly tried to see how I could mount the Dobsonian on the Equatorial Mount here on the right. Well, it sort of worked, but it sort of didn't. What would happen is, the way my Dobsonian was made, when you moved it around by kind of manhandling it, you would hear the tubes creak, and I knew the alignment was going on the mirror to the secondary. But I put up with that for a little while, but I really longed to have something a little bit more official, like a tube. So the next question for me was, how can I get to a tube? So back then, it wasn't very easy to find metal tubing. You didn't have an internet where you could just order stuff. Finding stuff locally was very challenging. You know, ordering things was even harder. But so I used to do a lot of boating. So I thought, well, maybe I could make one out of fiberglass. So what I did is I took a sonotube, a 14-inch sonotube. These are used in buildings. You can dig a hole, put a sonotube in the ground, and pour concrete in it. And this is sort of like a form, so that if you want to like mount a deck or have a deck sitting up, you could put this in the ground and you would have a firm footing for a deck. So what I did is I took this tube and I cut it lengthwise in half, in two pieces. And then I tried to think about how I was going to glass it. So one is I wanted a nice smooth outside. I didn't want some yucky thing. So I took a piece of Mylar, that heavy, thick plastic, and I lined it. And then I got my fiberglass. I used fiberglass mat and fiberglass resin. I'm going to shift to the next picture here. This is what it looks like today. And so I knew I wanted to have the inside black, and I thought I was really smart. And so I mixed up a bunch of tinted black epoxy resin. This is polyester resin. And I thought, well, boy, it's not going to really be so good having an outside black. So I didn't really want white because I thought that would be weird. So I went with gunmetal gray. So I mixed up some gray, had all my supplies ready, and I started to fiberglass the two sections. I got the gray layer done, 2 or 3 layers of matte. I mixed up my black and switched over to matte and black epoxy resin. And I coated both sides, and I was looking at it and I go, man, I just didn't know it was going to be so easy. That came together pretty good. But then I started scratching my head wondering, well, how am I going to put these two together? I mean, it's sort of a mess. And so I thought, I don't know, maybe I could really quickly cut the edges. The fiberglass mat was hanging over the edges, if you will. I didn't trim everything up perfectly. And so I thought, well, maybe if I trimmed it up really quickly and then sandwiched the two together, kind of taped or wrapped the two sonotubes together, and I thought, well, maybe I could get this done today. So that's what I did. I laid a couple of strips of fiberglass down the seams on the inside, and I just couldn't believe it. I actually got it done. It's pretty nice. I mean, you can see by the picture on the right that it's not perfectly spherical. It's mostly spherical. It could use a little bit of support on the two ends to kind of keep its shape a little bit, but otherwise it doesn't flex too bad. It's no lighter than a metal tube because fiberglass is not really all that light. And it's worked. So now I have, let's see, a mirror, a mount. I have a tube assembly. Fantastic. What's the next thing? Well, I needed to mount it somehow to the telescope. So this is a picture of my slip rings. So this is pretty fancy stuff. In equatorial telescopes, what happens is when you move from one portion of the sky to another, you'll find that your eyepiece can be upside down. Or maybe your eyepiece is like completely vertical on the telescope and your telescope's 4 or 5 feet tall, and you have to like get up on a short mini ladder to kind of look down through it. So I couldn't find really simple rings to mount it, so I found this guy making these slip rings. And so the red arrows point to the slip rings themselves, and the yellow arrows point to the supports that hold the two slip rings together. So the black part of the slip ring moves inside of the silver part. The black part is mounted to the telescope. Now you might laugh at my wood struts, but I always wanted to use something a little bit more special than wood, but you know, I started with wood and wood worked pretty good, so I stuck with wood. The reason why the yellow arrows have the support pieces that they're aiming at, I wanted to be able to unmount the telescope tube assembly from the telescope for transport. The whole telescope, I don't know, with counterweight, some 150 pounds or something, maybe a little bit more. And so I wanted to unmount the telescope tube assembly so I could roll it into the back of my SUV. So it would be protected. I mount the equatorial mount on the back of my SUV on the outside, just put a tarp over it and drive away. So the blue arrow points to a frame that I made so I can drop the tube assembly on top of this frame. I bolt it to the frame, and then I can wheel the frame anywhere I want, and then I can prop it up in the back of the SUV and kind of shove it in there. So it's worked pretty well. I've used it this way for, I don't know, 4 or 5 years. So now I've gotten all the way through slip rings. This is great. And the next thing was I needed a controller. So the original mount had for the RA direction is the direction that keeps you on track with an equatorial telescope, keeps you tracking on an object. So the RA direction was nothing but a motor with a plug. So there wasn't much ability to compensate or adjust or move things around. So back in the day, JMI was a pretty popular controller, and that combined with a stepper motor controller, I could basically control the 2 axes of the telescope. The 110 volt supply plugged in here, and then this stepper motor controller plugged in another location, and then I can control the 2 motors. Well, the problem with this is that back in the day, this would work fine with film photography. So when I started, people were doing film photography. You know, there was very little digital photography. They were extremely expensive. And so what you did is you had to man this control for an hour, pushing these buttons using a secondary eyepiece. You had your camera hooked into the eyepiece of the telescope, and you used a secondary scope or a finder scope, and you looked through that, and you used a reticle. That's a crosshair in the eyepiece. And you literally hit these buttons around as you needed them to try to keep a center, a tracking star, on center for an hour. So modern day, okay, move forward to today or the last few years, and we have a lot more devices. For example, we have computers that can do tracking for you. We even have elaborate controllers that can do tracking for you. So I really wanted to move forward into the more current year. So this is the next picture, and this is about my gearing. So I kind of scrubbed the old motor control. So on the left picture, you can see on the right one of the gears. That's the RA gear. And I tipped the telescope up 90 degrees so you could see the declination gear. So the blue arrow is the gear. The green arrow is the pinion gear, which is a small gear that runs the big gear. And then the red arrow is the stepper motor. Down below there, you can kind of barely make out there's actually a gear reduction there, a 4-to-1 gear reduction. On the right is just another picture that kind of shows the meshing of those gears. It's kind of interesting. Unfortunately, I've never been able to make a housing for it. The gear is so large. I think it's nearly 10 inches. And that's because when I first got the gears, the guy said, well, when you're doing photography, you want to have a gear as big as you can so that your accuracy in tracking and moving around the sky can be the best. So in today's times, you'll look at equatorial mounts, and you'll find most of them are no more than about 5 inches or so in diameter, maybe a little bigger, a little bit smaller. A lot more compact, a little bit easier to make a housing, and eventually I'll make a housing for this. So the next thing I needed to do, as you just see in the picture, is upgrade the gears. So then I have a little bit better motor mechanisms. And then the next problem I had is then I needed to make a controller. This is not a picture of a controller. This is a picture of the synchronous gear on the left, and on the right is the stepper motor. The synchronous controller, you put power to it, and then it just slowly creeps forever. On the right is a stepper motor. This works with 4 wires, and you have to give it a series of pulses, and the pulses make it step through 200 steps in one rotation. So by applying a series of pulses, you can get the motor to step in increments in a circle. So I picked stepper motors because they're a little easier to control. Most telescopes actually don't use stepper motors. They use motors, and what they use is a series of encoders to feed back the position. The problem with regular motors is how long you run it determines how far it goes, but it's kind of indeterminate exactly the ratio of how much time to exactly how far it moves. So what they do is they use a feedback mechanism which with encoders to know how far you move. When you move a stepper, you know exactly how much you moved it because you stepped it a certain amount of steps. Okay, now on to the controller. So this is my controller. The controller's on the left. It's in a housing. It's not too big. On the right is a hand control. It's a wireless hand control. And then the bottom is the heart of my controller, which is Arduino Mega. And I actually added so many functions, I actually need to upgrade the processor, this processor board to something a little bit more special. But I have a display in there, I have buttons, I have a joystick on this controller. Most of that I don't use anymore because I use the interface to the computer. The hand control is really nice because it's wireless, and I can set that anywhere I want. I can hang it by my neck, and then I can hit the buttons anytime I want. I use some buttons for slow, some buttons for fast. I have a button for turning guiding on. I have a bunch of other features that I put into my own controller. So the next thing is,
Hey, Al,
yes.
can I interrupt you? I have a question that came in. Is there a gearbox between the stepper motor and the worm gear?
Yes, there is. So on the left picture, the worm gear has this little worm gear and large gear. And then just below the red arrow, the green arrow, and the blue arrow is another set of 2 gears. So before it gets to the worm drive, I have a 4-to-1 ratio set of gears. It looks like a belt. It's a black line, a gear on the left and a gear on the right. And that's a basic gearbox. It's a belted system. Did I answer?
Okay, thank you. Thank you.
Okay. So now I have a controller, all the rest of the gear. I've got a fancy controller that I built. And the next thing is, in order to do photography, is I want to be able to communicate with the computer. The reason why is because there's several programs that you can use a guiding camera and have the computer interface between your computer interface between the computer program, the application, and your controller, your hand controller like this. And you can tell the controller which way to move the telescope to keep it on track. Now, for some of you, these are all like a lot of rehashing. But for me, of information you already know. But for me, I've learned this all through progression, through trying to add features and try to bring mine up to speed to where a lot of store-bought telescopes are today. So the next thing is I needed an interface to make those two communicate. So the top 2 pictures come from the ASCOM website. I don't think they do a very good justice to exactly what's going on. But essentially, the ASCOM interface is a protocol that uses wires, and it uses this protocol to attach several different devices or several different telescopes to one computer, or to send that information to several different computers. So it's cross-linkable. You can have 2 programs running on one computer that both reference the same telescope and the information coming to and from the telescope. So it's a really unique interface. It is what the world really needed. I don't know when it was created, but up until then, you basically could have one computer and one telescope. So down below on the bottom level here is a little bit of the communication protocol. So the command is something that the computer sends to the telescope. It sends in this case, it sends it by RS-232 or a USB connection, but it sends it in text. So it sends a colon, a G, an R, and a number sign. And what the telescope replies with is HH is the hour, so it could be 1 to 24, and then a colon, minutes, colon, seconds, blah, blah, blah. So, for example, in Stellarium, when it's tracking your telescope movement and where you're positioned, it polls your controller periodically with these 2 commands in order to see where it is pointing. The telescope doesn't send it automatically. Stellarium has to poll for it. On the right is movement commands. There is a MN, move north, move south, move east, move west. And then in most controllers, it's done by pulse. So the application, or Stellarium, for example, wants to move the telescope. It sends an MN command. Then it waits a certain length of period of time, and then it sends a quit command. Down below is the QN, QS, QE, QW, and those are quit commands. So instead of saying move a certain length of time, it says start and then stop, move and then quit. So that's just a little taste of how these protocols work. There are a lot of other commands, and some telescopes use all the commands, and some telescopes just use a small subset. So,
Al,
yes.
I have another question. On your Arduino board, is that code that you've developed yourself, or is that something that you've pieced together from other code?
Well, I started it years ago, and actually I developed it 100% by myself. There is, I know you're using some code that's online. It looks like really good code. I did add code from other things. For example, we haven't gotten to it, but I added encoders. I had to add a real-time clock to find out local side real-time. And so there I did use some code from other people. Some of that code can be very complicated. One of the problems of using my own code is it's not exactly right. The problem with using somebody else's code is if it doesn't work right, you don't know, well, how they did it. So yes, it is my own code, but I'm still in the process of debugging small issues with it.
Okay, thank you.
So we're going on to a new picture, a new slide. And this is a picture of Leo. There's a few galaxies here. This is Leo's triplet up in the top center, and then down to the middle right are a bunch of other clusters of galaxies. I can see in my 12.5-inch telescope a reasonable number of small galaxies. The problem I have is that I star hop. So I go point to, let's say, this star here, I think it's called Charton, and I will go and find that star, and then I will use my Telrad viewfinder, and I will move over to where I think Leo's triplet is, and I probably am not dead on it, and then I move it around till I find it. So it's become very irritating with a telescope that can see small galaxies to figure out exactly which galaxy I'm looking at. I'm not really fond of looking at star charts. So I wanted to get the positional data on my telescope. And the way that's achieved is you put things called encoders on the telescope. Encoders are devices that can tell you the position of your telescope. So I'm going to flip to the next picture. So this is a picture of an encoder. So on the right is the outside housing, and this is a really standard encoder people use. It's made by US Digital. They make them with many different steps and increments and all sorts of different types. On the left is an exploded view of the inside. It uses a light source and then a code disk, which basically is a number of slits, and then a photodetector assembly that as the wheel spins, it causes the light source to pulse. And with your controller, what you do is you count the pulses. So you start at 0 and you count up. In my case, I'm using 15,000 incremental encoders. Most people use around 15,000 to about 30,000. Just depends on how much accuracy you want to work with. And so I'm going to show you a little bit more about how this works mathematically, but I just wanted to show you what the apparatuses look like. So the next slide is a picture of Stellarium. I've really been fond of Stellarium, especially since it's free. And so I set up my encoders hardware-wise on the telescope, and now this is how it works operationally. So within Stellarium, you can set up telescope control. And when you set up the telescope control, you tell it that I'm going to communicate with XYZ telescope, through the communication channels, usually by COM ports. And then you can label it. I label it 12-inch Meade telescope, even though it's not a Meade. And when I turn on my telescope, the encoders are set to 0, 0, 0, 0. So necessarily, it aims at Polaris. So when I turn everything on and I get my controller working, all my interfaces going, this is the position that it starts at. And so that's just above Polaris. So the next thing I do is I find a guide star, not a guide star, an alignment star. What's really neat about Stellarium is you can use it to do alignment. Now, there's a tricky way to do 2-star alignment, but for right now, I'm just doing a 1-star alignment. So the way it's done is you pick a star, and now to the right you can see in Draco, I picked the star. I don't know the star by heart, TYL. And what I do is I say, well, that's my star. I aim my telescope at that star, and then I pull up this screen. This is a SLU2 telescope screen. It's used, you use Control O to find it. It's obscure. And what I use this for is I can set the current object, which is this star. I hit the current object button. It brings up these right ascension and declination coordinates. And then I hit the sync button. What that does is it tells my telescope to set its position to this star's location, these coordinates. And what I do is I take that number and that information and I set my encoders to this location. So my encoders need to be initialized to some value. I can't align to the Polaris, so I have to pick some other star. So what I do is I use the sync button. It sends the command to the hand controller, and the hand controller says, oh, I'm going to set my encoders to this number, and that's going to represent this right ascension and this declination. And then when Stellarium polls the hand controller, it repeats back that same number. So now you see my 12-inch Meade telescope is aiming at the star that I picked. Hopefully that's straightforward. So now, whenever I move the telescope around the sky, this 12-inch Meade telescope, what do you want to call it, avatar, if you will move around the Stellarium's viewport wherever I'm aiming. Do you believe me? Well, it's tricky. It's been a lot of work and a lot of pain. But I'm going to show you, I can't remember what order I have. So the next thing I'm going to do is, so I basically got my encoders to work. I have a fully operational telescope. I can tell where I'm pointing. So basically, I've arrived at what most store-bought computer-controlled telescopes can do. I don't have a big library in it. I'm depending on Stellarium and other objects to help me point in the right direction. But I did home build it, and it's been a great learning experience. Today, would I go buy a newer telescope and a store-bought one? Probably. But I did have this from 20 years ago, and I have been able to bring it forward into the modern age. And so it's been very interesting. The next part of my talk, I was going to devote to a little bit of something fun. Everybody likes math and astronomy talk, right? Let's see, we're at half an hour. Let's see if I can do this in about 10 or 15 minutes. So I'm going to start with a basic picture of coordinate system. Most of you know this because you use these terms all the time, but it's really mystified me, these terms like right ascension. Where did they get this name from? I mean, I'm not that much of a scientist. So I looked it up, and I did find on one website finally where this terminology came from. I'm going to tell you. The Babylonians began their calendar year on the first new moon after the vernal equinox. The vernal equinox is an occasion marked by an elaborate festival as the goddess Ishtar, ceremoniously resurrected from the dead after her body spent 3 days and nights in the shadowy underworld. Perhaps following the Babylonians, the Greek astronomer Hipparchus created his celestial coordinate system and set the vernal equinox as the point where the celestial coordinate system begins. This is 0 hour. And we say that the vernal equinox has a right ascension or an RA of 0. I think about the RA, or the right ascension, as the direction that the Earth is turning underneath the sky. And in electronics, we use a term where you stick your finger out and you put your thumb in the air like you're holding a gun, and then you stick your finger out to the left. And this is supposed to indicate if you aim your finger at the North Pole and you aim your finger in the direction of the Earth rotate to the center of the Earth, that it'll rotate where your middle finger goes. And that's an electronic way of determining kind of your right from your left, if you will, in directions. But anyway, so I want to start off with the coordinates. And the biggest problem about coordinates is the difference between absolute and relative coordinates. And when you're building a telescope, that's what becomes the most important. So I'm going to start with the difference between an alt-az and a equatorial mount. So on the left is an alt-az, and it's denoted by, if you look at the telescope, the base is sit flat on the ground essentially, and then there's a thing called altitude, which is the circle that looks like it goes left to right in a circle, and that determines how far up the telescope is looking. On the right is an equatorial telescope. The base is not sitting flat. The base is set at the latitude, or the angle that Polaris, or the center rotation of the planet, is rotating around. I don't know, we're somewhere around 30 degrees or 31 degrees, I think. And so you would aim this at 30 degrees up in elevation. And then the same as the alt-az telescope, the up and down direction is the same on the equatorial mount. But what the equatorial mount does is, because it's aiming at the center of rotation, you don't need to change the declination very much. You just have to change the RA as the Earth spins. So what does this all matter? Well, if you're looking at an object, you want to stay on that object, so you have a little motor that keeps you there. If you're doing photography, you want to be able to keep tracking on that object perfectly so that you can get the most perfect picture without any smearing or blurring. So I brought up this idea of absolute coordinates versus relative coordinates. And this is what gets tricky. So things like Stellarium, they like to tell you where the objects are in an absolute coordinate system. All the libraries, like before we had Stellarium, we had to use paper maps. We have diagrams of all of the stars and all the objects that are not moving, that are set in a sphere that gives us the declination and RA for each of the objects. Sometimes you have tables, sometimes they're diagrams and pictures. But what happens is, since the telescope moves, it likes to operate in the relative world. So somehow or another, we need to convert between absolute and relative. So here I'm still picking on one of those stars in Cassiopeia. I'm going to use Cassiopeia in the last part of this talk. And so I assume that most of you all know that RA is like longitude and declination is like latitude. Let's see, I can't remember what the next slide is. So what I did here was I basically zoomed in on the Stellarium window so you could see more of the numbers. And so this is done pretty early in the morning tonight. I changed the time in Stellarium so it'd be very much early in the morning. And the green arrows toward the right show 1H and 2H. This is the RA, this is the HA, hour angle. No. The RA, hour angle. So the yellow arrows are pointing at the declination, and the far left one says 30, 40, and then they go all the way down to the center where Polaris is and go to 90 degrees. So if we look at Cassiopeia, where I have the red arrow, then you go over to the left side of Stellarium, it says RA dec J2000. Well, that's the absolute coordinates of where this star is. But the relative position is through 2 lines down that says HA and dec. The declinations are the same, but the hour angle is different. And the hour angle depends on what time of the evening it is. So I'm not going to go through this in real great depth and detail, but down below are some of the equations. So what I use in the Arduino is I use a real-time clock that's set to our local time, and I read that time, and I need to find what's called LST, local sidereal time. Sidereal is a term related to the sidereal rate, the rotational rate of the planet. But we need to find the local time. So on the left-hand side, I start with the time, and I have to justify that to the year 2000. And then I'm not going to tell you what all the rest of these terms are, because this is what I got from some other code. I verified that it works right. But basically, we're trying to get to Greenwich sidereal time, and then Greenwich sidereal time gets converted to local sidereal time by your longitude and your sidereal day. A sidereal day is not 24 hours. It's just shy of that. I was looking to see, I wrote it down. It's something like 24 and a half. It's like 24 3/4 of an hour. So we get LST. So what we want to do in the telescope is figure out what the relative position is. So we want to develop this term called HA, which is hour angle. So we use this equation, hour angle equals LST minus RA. So the RA is the absolute time, location of the star, and LST is our time, and HA is the relative position. So why do we need to know this? Well, I talked before about encoders needing to be set to a certain value. And what I need to do is be able to set my encoders from the relative position and then be able to convey to Stellarium the absolute position. See, Stellarium only communicates in absolute. It doesn't communicate in relative RA and declination. So here's how the encoders are set up. So on the left, this is a diagram. So on the left is the sky declination. Declination is much easier to understand. So these concentric rings are degrees. So the pole, the very top of our planet is 90 degrees. Then it comes down in concentric rings 80, 70, 60, 50 until the celestial equator, which is 0. And then it flips from 0 and goes negative and goes to negative 90 degrees down at the South Pole. So on the right is how the encoder works. So the encoder, I told you before, mine goes from 0 to 15,000. So above it says 90, that's 90 degrees, and that's set at 0 or 15,000 counts. On the left is the 0, the celestial west, and then the right is celestial east. So this is a diagram of how the encoder spins and what the different places on the encoder would represent. So on the left-hand side, you see an A. On the right-hand, you see an A. And so if I was to point at the RA of this line, 60 degrees A, then I would want to set my encoder value to 1250. So what if we aim something at the same declination that's over here at C, and we need to set our encoders to that value? Well, when I move the telescope, I'm actually pointing way over here at 13,750. Uh-oh, there's a slight problem. The problem is the numbering system. The encoder wants to go in a circle and count from 0 to 15,000, but the sky is not arranged from 0 to 360 degrees. It's arranged from 90 degrees to 0 and then to minus 90. So there's a translation that has to go on, or has to happen. And that's done through formulas. And that I'm not going to bore you with. You would hate that. But maybe at another time we could go over that. So this is probably going to raise some questions or have a lot of people not really sure about what I'm saying. But I'm trying to plant a seed so that in the future you have a better feeling for what's going on. So in the RA direction, we have a very similar type of arrangement. On the left-hand side, I set the diagram here to 8 p.m. our local time, and that is a HA of 16. How do you get there? You take 20 hours. Our local deviation for our time zone is -5. And then we have to count for daylight savings time, because we use daylight savings time in this time zone. So to get to 16, we take 20 hours, which is military time for 8 p.m. We subtract 5 and add 1, and we get 16. So in the sky, we would look above, and we would be at HA hour 16. But so if I come over here to the encoder, I find that I set my encoder is set at 0 is 24 hours or 0 hour. And then what number would I pick for 16 hour? Well, I would take the equation of 15,000 divided by 24, and that's how many ticks I have for every hour. And then I'm at 16 hour, and then I multiply times 16, and that gives me 10,000. So if I was aiming at this location, I would set my encoders to 10,000. I know that this is a little bit confusing, and the sidereal day is 23 hours, 56 minutes, and 4 seconds. The reason why I put that on there is because when I said 24 hours, it's not exactly right. It's really 23 hours, 56 minutes, and 4 seconds. So this is where the math gets a little bit shady and gets a little bit complicated. So I'm going to move on to the next slide and leave you wondering. So this is the crux of the problem. So I can move the Equatorial Telescope all the way around the sky, but what ends up happening is an Equatorial Telescope flips. So I'm starting in Cassiopeia on the eastern part of the sky. Polaris is a little bit to the left of it. And when I revolve the telescope around or follow Cassiopeia around, I go to this location, which is the Equatorial Mount now is completely on its side, and Cassiopeia is right above Polaris. And what's happening, if you look down at the mount, is my telescope just about to run into the pier that it's standing on. So I have to fix this problem because one is I can't go any further. The second thing is when I spin it around to the other side, look what happens. Okay, I've spun it around to the other side, and now two things have happened. My RA has completely changed 180 degrees because I flipped it 180 degrees, the telescope. The other thing is my declination has changed. I used to be a positive like 1250, and now I'm positioned at 15,000 minus 1250, which I forgot what that number is. 30, what did I say? 13,000 something. So this is what happens in the math is you have to account for your telescope flipping in an equatorial mount. So this adds another little thing to the mathematics. So what I do is I detect when I flip through 0, and when I flip through 0, I have to make a modification in the numbers. I have to now start subtracting from 15,000. When I flip through the zenith, or the HA hour overhead, then I also have to do modifications to the RA numbers. And I looked at other people's codes, and they do the same thing, but I was very confused by how they were doing it and exactly what it meant. So I sat down with the equations and figured it out and made modifications until I got it to work right. Dead silence. So that's called meridian flip. And here I've moved the telescope a little bit further. So I started on the east side, I went through the zenith twice, and then I ended up on the west side, and now the telescope looks a little bit more normal. But from here you can see when Cassiopeia was on the right, I had the telescope aiming to the right. So I'm done, essentially. I ended with the picture of my telescope. So the gray gun barrel, the large part, is my main tube assembly. The smaller tube is that 4-inch tube, which I use as a guide scope. What I didn't talk about was down here below this white object is my counterweight. I didn't want to mail 45 pounds of weight through the mail, so I built my own using lead shot in a plastic tube. And I didn't tell you, but I did most of this back in the 1990s. And it sat in storage for about 10 or 15 years. And I finally said, I'm going to take this out of mothballs. I'm either going to use it or I'm going to sell it. And I put it back together. I added some features as you've heard me talk about. And it's really worked out nicely. I'm so happy I met you all, and I've been able to go to star parties here in Texas because I've both learned a lot and I've been able to further the quality of my telescope from the knowledge and the expertise of everybody else. So I just wanted to thank you all.
Hey, Al.
Yes.
So when we were out at El Dorado, this is a question from Brandon. You were working on your tracking when you were at El Dorado. Where are you on that?
Well, I ended up with two problems. One is, you would think with all those gears, I would know exactly how many teeth there are, and I would know exactly how fast to move it. But I have yet to figure out exactly how fast to move my telescope. The second thing that I found out is the quality of my gear meshing is not all that superb. And so I'm in the process of reworking how my gears mesh. I've been able to get to about 9 arc seconds, 10 arc seconds or so. But Doug reviewed my data and said that I need to get it closer to like 3 to 5. And so I'm in the process of getting that to work. Last time I was there, I spent 3 nights doing nothing but working on software. That was painful.
Okay. Next question. Are the encoders directly connected to the axis shaft, or is there some kind of coupling, like a gearbox between them?
Yeah, excellent question. Well, in a lot of Aldaz or Dobsonians, it's very easy because you have easy access to the 2 poles or the 2 rotational axes. The problem with equatorials is there's no direct way to connect it to the center of the shaft of movement. And so what I did is I had a machinist friend of mine make me a big round circle that I mounted to my gear. And then I saw this design online. And then I took a belt and I flipped it inside out to make a gear. And so basically I use a gear about 5 inches in diameter, and I use a small gear to mesh the encoder with that gear.
Okay. Another
So,
question.
no,
How do you keep...
so the answer is no, I'm not using friction, and I created basically a gearing system in order to gear the 2 together.
Okay. Next question. How do you keep the lead shot in the counterweight from moving around?
Excellent question. Well, you know, it's a work in progress. And the lead shot was a quick and dirty solution. I wanted to use lead because I cut the length of the axis that the counterweight sits on, and I need a lot of weight. And so I was looking for the weight to volume situation and tried to pick the thing with the most amount of weight in the smallest amount of space. And I thought about adding wax in there. Wax is a good simple way to kind of glue it all together.
Okay. And finally, when and where is your next attempt?
When and where I what?
Is your next attempt at getting it all running?
Oh, well, the big news is I ended up buying a 25-inch telescope last month. And so now I have 2 telescopes. I would love to get this telescope to do a little bit of photography. And the 25-inch telescope's a wonderful visual telescope. And so I am planning on going to El Dorado in September. However, Doug's been sort of lightly twisting my arm to go to Okie-Tex. But after that, I will probably both be at Fort McCavitt, and I will definitely be at El Dorado this fall.
Okay.
El Dorado
You had lots of comments about a great presentation, and I'm going to go ahead and pass it back to Doug. Thank you.
Thank you.
Doug, you have a go.
Okay, thank you very much for that presentation, Al. And obviously, you've put a lot of work into that. That is an incredible feat of achievement. Now, as many of you know, if you've ever attended any of our meetings, you'll know that I normally introduce the main speaker before he talks. But my great apologies to Al. I left your bio in the other room, but I have it now. And so I'm going to read Al's bio after his talk instead of before it like I normally do. So here's the bio introduction for Al, which we will do at the end. So Al Mallory worked as a hardware design engineer in Silicon Valley for 20 years. He designed and tested circuit boards and designed field programmable array chips. He worked for Intel, Cisco, and many other startup companies. Once he moved to Texas, he started mining and faceting sapphires, designing jewelry, and selling to wholesale companies. So again, my apologies, Al, that I forgot to read your bio before. Couldn't do it because I left it in the other room, but thank you again very much for that presentation. Next up, we have Kayla LaFrance with James Webb, a photo introduction. Take it away, Kayla.
Kayla, you have a go.
All right. Hello, everyone. I think you guys probably remember me, Kayla LaFrance. I'm here to talk a little bit today about James Webb. Really, we're just going to look at the photos that got released. I'm sure most of you guys have already seen them, but just in case you haven't, I would like to go ahead and share them with you guys. So I think everyone kind of has a general idea of the Webb and its main goals, but we'll go over them real fast. Basically, the main goals for the Webb are 4 of them. Number 1, search for the first galaxies or luminous objects formed after the Big Bang. 2, determine how galaxies evolved from their formation until now. 3, observe the formation of stars from the first stages to the formation of planetary systems. And then to measure the physical and chemical properties of planetary systems, including our own solar system, and to investigate the potential for life in those systems. The James Webb Space Telescope is an orbiting infrared observatory. It's approximately 60,200 kilograms, which is around 13,600 pounds, excuse me. Aperture is equivalent to around 82 square feet. It's beryllium coated mirrors, or it's beryllium mirrors coated with glass. It's a Friday, y'all. It's beryllium that is coated with gold to make the mirror segments. It is 1.5 million kilometers from Earth, orbiting at the L2 Lagrange point. That's equivalent to 932,000 miles. 100,000 miles. Operates at under 370 degrees Fahrenheit. All right. And then now I found this really cool animation that NASA has for, I need the arrow. I need an arrow. There we go. This just shows you how the orbit works for the L2. If you guys haven't seen this, what's great about the L2 orbit is that while it is going around, it has the ability to use its shield to block the sun at all times, but also it's still able to communicate with Earth at all times because it is always communicating or facing Earth in that sense. So that's really cool about the L2 orbit. All right, but let's get to the pretty stuff. The first images that were released on July 12th. The first one that they released was a deep field. Now, this was the teaser image. They put it out a few days early. This is SMACS 0723. This was a gorgeous photo. I'm sure everyone has looked at these. I will give you the link to the website where you can go find the high depth, high resolution and like zoom in on all this. It's crazy. But you see gravitational lensing, you see a couple of stars and just a plethora of galaxies. I mean, just so many galaxies. It's amazing. This is the same deep field that Hubble has also produced. So this is what Hubble versus the James Webb Telescope looks like. Hubble being on our, I guess that would be the left side of the screen for you guys. And the James Webb Space Telescope here on the right. Much brighter, much more detail. It's amazing. Oh, jaw-dropping. I'm sure y'all were just as goosebumped and exciting. So what is SMA? Do they call it SMACS? I'm going to call it SMACS. That sounds easier to say. SMACS 0723 is a galaxy of a cluster of galaxies about 4 billion light years away from Earth, and it's within the southern constellation of Valens. This is not a constellation I'm familiar with, but I got the photos here for anyone lucky enough to go down south and want to look for it. I did not find an equivalent photo from an amateur because I don't think it's a little bit beyond our ability. So let's look at the next photo that came out. That was the Southern Ring Nebula. And again, jaw-dropping, y'all. Phenomenal. Oh, gosh. It just, the detail. I cannot express how amazed I was by the detail. So this is the James Webb photo versus the Hubble. James Webb this time is on the left side with Hubble on the right side. Again, the depth that they're able to get in the images is much greater. You can see that the planetary nebula side of it, it extends much further out. There's just more detail. There's more contrast. The color is much different. And I don't work with the James Webb, so I can't tell you how that all is happening, but chef kiss, right? So the Southern Ring Nebula, what do we know about it? It is also known as the 8-burst nebula or Caldwell 74. It is a planetary nebula in the southern constellation of Veil. Its distance from Earth is estimated at around 613 parsecs or 2,000 light years. If you wanted to find it in the night sky, you'd look for Veil. This is the constellation right here. And you actually can find it on a lot of maps. It's indicated right here at number 3132. I believe that's its NGC number. And so it is one that amateurs do see a lot. It is on a lot of main maps. If you were to look at it with some amateur equipment, this is an astrophotograph I found of it by an amateur. I did not catch what gear they were, or what type of equipment or size of telescope they're using, but you can see the same shape right there. You can kind of see the same general concept. And then this was with a little 10-inch, and it was just a little Cheerio, a little fuzz, kind of like when we find the Ring Nebula on our own side, M57. You know, you get excited when you see that little fuzzy Cheerio. So that's what we would see. We don't have the James Webb or the Hubble. Next up was Stephan's quintet. This is one that we've seen at the George. So if you've come out to the George Observatory, we have shown this, and this puts the George to shame. Again, so much detail. You can see all the different galaxies, and then the garbage. Look at all the garbage in quotations. Just galaxies galore. Everything in the background is just hundreds of galaxies. And that's one of the things that's just been beautiful to see, is just how many galaxies are behind everything that we look at. So what does it look like? Hubble versus James Webb Telescope. Hubble is on the left this time. James Webb on the right. Again, you're just seeing more definition, more contrast. Contrast, definition, a lot more of that. And also you're picking up so much more of the background. Such a beautiful photo. What do we know about this quintet? It's a visual grouping of 5 galaxies, of which 4 of them actually form the first compact galaxy group ever discovered. So one of the galaxies is actually further away, but 4 of them actually are interacting with each other. It is visible in the constellation of Pegasus. Yay, a northern constellation. And this was discovered by Edward Stephan in 1877 at the Marseille Observatory. And if you were to look for it, you'd find Pegasus. Pegasus is easy to find. Usually you find the big square with the little legs, and then you can find it just above what would actually be his lower leg, because, you know, he's upside down in the sky for us. So you find his lower leg, and then you'll see, you can go up here, star harp a little bit, and go find the quintet. What would amateurs see? This one here, I found this image right here that was taken by an amateur. Again, I did not get what he used, but I did get that this one here was on an 8-inch Dobsonian telescope when they drew what they saw. Again, not as big in a high definition as the Webb or the Hubble, but it's still, this is something fun to see that like I said, we see it at the George a lot. The next one was Karina Nebula, which, oh my God, the color was so beautiful on this one. I was at NASA when they were showing all of these, and just every office, you could just hear the gasps and the oohs and the ahs through the hallway. So this is Karina Nebula. If we want to compare it from the Hubble versus the James Webb, Hubble is on the top, James Webb is on the bottom. Again, we got the same kind of thing going. We got better contrast. We got, I think, almost better color. We have more details. Absolutely phenomenal. I cannot wait to see what else this telescope's able to bring to us. How do you find the Carina Nebula? This is also known as the Eta Carina Nebula. It is a large complex area of bright and dark nebulosity in the constellation of Carina. It's located in the Carina Sagittarius arm of the Milky Way galaxy, and it is approximately 8,500 light years or 2,600 parsecs from Earth. So if you were looking at Carina, which is Canopus, I think, is the only thing I have seen from here in Texas. Being a northern girl, I have not seen much of this constellation myself. But if you follow it to the end, it is actually right here with next to the little Eta. And also it is 3372. So that little square, green square, you will find this one also indicated on most standard astronomy star charts. And so then amateurs, what do they see? I found this one picture here. I do not have what they used on there for this photo, but for this drawing that we got here, this was using 15 by 70 Oberwerk binoculars. So a decent size astronomy binoculars, and they were able to get nebulosity for the primary structure, and also I believe there's like a little secondary structure right here, it looks like. So yes, this is also an object we can see. This was a new one that I wanted to throw in real fast. I don't know if you saw this one. This was not part of the big release. This actually came out on August 2nd. This was the most recent photo that has been released. It is the Cartwheel Galaxy. James Webb Telescope versus the Hubble. More detail, more contrast, more background stars. Well, actually not stars. Forgive me, galaxies. And what do we know about the Cartwheel Galaxy? It's a lenticular galaxy and ring galaxy about 500 million light years away in the constellation of Sculptor. Estimation of the galaxy's span is around 150,000 light years. And if you wanted to find this constellation, again, southern sky, they really are like in the southern skies right now. I'm going to assume that's just based on like orbital mechanics right now. But if you're looking for it, Sculptor is easily seen. Sorry about that. Easily seen if you find the triangle here. And then what you're looking for is approximately right about here. It's about halfway through the line. The bottom line here is where you would find the Cartwheel Galaxy. And I was able to find some evidence of people seeing this as amateurs. Here's a photograph that I found of it, and here is a telescope drawing I found of it. And I didn't capture what telescopes they were using for these. But I would assume they're a little bit bigger. I didn't get what size it was. I'm not going to guess what size telescope they used. Sorry, guys. But if you want to follow the mission there, so the high resolution photos you can find at www.nasa.gov/Webb's-first-images. Detailed information about each photo in high resolution. I've downloaded them. I have zoomed in on them. I've played all around on them. You can also find more information on the mission at jwst.nasa.gov. And then also, if you follow Twitter, that is where they announce the new photos. So go to Twitter, follow them at NASA Webb. They will pop every time a new photo or a new announcement is. That's usually where I find out most information, is I get a notification that they tweeted on Twitter. And that's my slideshow.
Kayla, thank you.
Yes.
On Webb, here's one of the questions. On Webb, I heard they had there was micrometeor damage. If true, do you know how large the actual damage was, and is it on the main mirror?
That is the first I'm hearing about it. So I can look into that. Anything I would know is whatever is released to the public. I don't work the Webb side of the mission at all whatsoever. So I can look into it, but honestly, that's the first I've heard about it. And I do chat with people who do work this mission, and they haven't mentioned it. So I'll look into it. That's all I can say, and see if I can get a hold of you. Let you know. Let's see. That was Doug who asked.
Yeah, Doug asked. Yeah.
All right, I will. I'll look into that and see if I can find out. But no, that's the first I've actually heard of that. So sorry, I don't have an answer for you.
All right, thank you, Kayla, and glad to have you join us this time. I'm going
Yeah.
to switch back to Doug. Doug, you have a go.
Okay, Kayla, thank you very much for that most excellent presentation. Okay, next up, I have a DIY astronomy, astro imaging automation. So, astro imaging automation. This is the phases that you kind of go through when you're doing astrophotography, astro imaging. I'll call it phase one is when the astronomer and the telescope are both outside. So in that case, you know, the astronomer's out there and you have to deal with heat and cold and mosquitoes. And in my case, the local neighborhood raccoons that want to come up and be friendly to you that you don't necessarily want to be friends with. Phase two, the astronomer is inside, the telescope's outside. One little bit of improvement, you're inside, but you're still up, you know, all night making this whole thing go, even though now you're inside and the telescope is outside. And you can avoid all the weather and other things. Phase three is where we kind of want to get to in automation. The astronomer's in bed sleeping and the telescope's outside taking pictures. So that's the goal of astro imaging automation, and that's what I'm going to talk about tonight. Is phase three, a way to do this. Okay, so not too long ago, I was taking this picture of the Veil Nebula. And if you're not familiar with the Veil Nebula, this is NGC 6960 down here. This area is called the Witch's Broom. Kind of looks like a witch's broom. There's a broom area and there's the handle maybe. And then this area up here in the upper right-hand corner is called Pickering's Triangle. But because I'm doing this from my backyard, which I live in a Bortle 8 skies, I have a street light out in front of my house, I'm doing narrowband imaging. It takes a really long time. The integration times are very long. I think this one, 15 minutes for each sub, and there's a whole bunch of them. So I've got a total of 15.5 hours. These are hydrogen alpha and oxygen 3 images combined, and this was over 9 different evenings. So as you can imagine, we don't really want to sit out in the backyard for 9 nights, you know, in the weather and everything to get an image like this. So it would be great if we could figure out a way to automate this. And I'd heard, you know, other folks in our club have been doing this. Chris Wells specifically, I think maybe Trevor has, I'm not sure about that, but Chris has for sure done this. And so since he had success with it, I thought maybe I'd give it a try too. Okay, so here's the configuration. Outdoors, we have a Raspberry Pi that's in a shoebox. I like this because you can open and close the shoebox and open it up, fiddle with the Raspberry Pi, close the shoebox lid and keep the dew off of it. And then the telescope configuration for the image I just showed you. This is an 80 ED Celestron imaging scope with a field flattener, the hydrogen alpha and oxygen filters, and then I've got a custom-made KF 8300 Kodak CCD base camera. Then there's this little Orion guide scope on here, one of the 50mm guide scopes, and then a custom-made MT9 M034 CMOS-based guide camera. So that's not really all that important for my point tonight, but just to show you what the configuration was for this particular image. I just wanted to show that to you. But the main point is, how do I do this automation so that I can go in and go to bed and let the thing run all by itself and not have to be up with it one way or the other? So I'm going to show you 2 slides that shows how to do this. So I've got the Raspberry Pi running out there, running the computer, and then remotely I have an indoor laptop that is running K-stars and ECOS. So ECOS is the telescope and camera control tool that comes with K-stars, that's part of K-stars. The nice thing about the K-stars and ECOS world is it's free. That's a good thing. The bad thing about K-stars and ECOS world is it's a little slightly challenging to figure out how to get it all to work. But once you get it all working, it amazingly actually works really well. Once you get it working, it's surprising. And the point of my presentation, one of my points is that when you first look at this, it's hard to believe this is actually going to work. You look at it and you think, that can't work. That's going to malfunction. It's going to have all kinds of issues. But the truth is, the very first night I tried to do this, it worked perfectly and had no issues. And other people have reported that they've had good luck with this too. So amazingly, it works. So here's how you do it. When you're in ECOS, first thing you do is you click on this little camera icon here, and you set up your exposure time, which here's my exposure time, 900 seconds. You set up the count, how many you want to take. I took 2 images, and then the name of your thing. So I got NGC 6960 Pickering's triangle, hydrogen alpha. So you create this thing in this screen, and then what you do is you save this as a .esq file, which is going to be needed in the next slide I'm going to show you. So you create this, telling us how long are my pictures going to be, how many am I going to do. I save it as a little file, which I'm going to use next. I go over here to this other tab. I go to this tab that looks like, I don't know what that is, something. But the name of this thing is Object and Sequence Selection tab. And I don't know what that graphic is supposed to be, but oh well. So I take my ESQ file that I just made. You go and you navigate to that and you stick that in here. And then you take an image file that you've taken before. Now, it is true that you have to take at least one picture of this object in order for this to work. So I have some picture that I already took with the same camera and the same telescope of this object. It's got my framing, how I want it, and all orientation and everything. And amazingly, what this is going to do is it's going to use this picture that you took before, and it's going to go and align your telescope up and you know, almost perfectly align it and frame it just like your other pictures, so they're all aligned exactly the same. And this is going to do this based on a previous picture that you load right here that you took in the past. Okay, so step 1 on this is you tell it the start time. So in this case, I told it it's going to start at 2 a.m. This is when this whole thing's going to wake up. It's going to sit out in the backyard. It's not going to be, you know, doing anything. And at 2 a.m., the whole thing's going to wake up and start doing what I want it to do. Step 2 is it's going to unpark the mount. So when the telescope is in this position, means counterweight down and it's pointing to the north, that is its park position for this particular telescope. But when this whole thing starts, it's going to say, okay, I'm in park. Now what I'm going to do, I'm going to unpark the mount and we're going to get going. Step 3 is going to slew to the target and track. You've told what the target is here by this image file. It's going to slew over there. It's going to figure out what it's supposed to be looking at. It's going to start slew to that target. It's going to start tracking. Then step 4 is plate solving. And plate solving is where the camera and telescope are going to take a bunch of pictures and they're compare them to this other image that you already took. And it's going to move this thing around until the telescope and the camera are pointing exactly the same. That's what plate solving is. So it's going to line it and get it all lined up. It's going to plate solve by clicking this. Now, I didn't click focus. You can actually have it focus too if you have an electronic focuser, but I didn't do that. The step 5 is calibration auto guiding. Once it's pointing at this thing that you want to take an image of, then step 5 is going to start your auto guide. It's going to do the calibration. It's going to start auto guiding this whole shebang. And then step 6, once this is all done, once it's taken those images, like I set up to take 10 images, once it all gets done, down here it's going to go back and it's going to park the mount, and it's all going to be sitting there just like it started for when you get up the next morning and all your images are going to be done. So this is all there is to it. And the first time I looked at this screen that you're looking at now, I looked at this, I thought, there is no way this could possibly work right. There's going to be something that's going to malfunction. But I have to tell you, it worked. I've used it for 9 evenings to get this image, and it worked perfectly. And I'm going to use this in the future. I'm going to sleep more, and I'm going to have more fun taking more pictures because I can automate the whole thing and not be up all night with it. So there you go. Now, there's lots of other ways to do this. There's other software that will allow you to do this. But the thing I like about this is it's free, and it's kind of just interesting that you can actually do this with a Raspberry Pi out in your backyard. I like that, but it's kind of a little challenging to get to work, but it is free, so I think it's kind of cool. So I wanted to pass that on to you guys to make you aware that this exists, and maybe you'll want to try this too sometime. And here's the picture again. I'm sorry, what?
Oh, Doug, yeah, there was a question. Which
Right.
auto guide is being used
I'm
by
using-
selecting the auto guide button there?
I am using PhD2. So I'm not using the internal guider with that ECOS has. I'm actually using a PhD2. And a PhD2 is actually running on the Raspberry Pi. It's actually not running on the laptop.
And on that icon, I think that's supposed to represent one of those old school day planners, a scheduler.
Okay, well, okay, I believe you. I had no idea. Oh, that's a good idea. It looks like a planner, doesn't it? Yeah, okay. I can believe that. Any other questions?
No, but it sounded good, right?
Yeah, no, I believe it. Okay, the thing about PhD2, I know you can use the internal guider or PhD2. I like PhD2. A couple things is it lets you do multiple star guiding. And actually, Brandon mentioned this to me a few months ago, and I kind of heard about this, but I hadn't done it. But he was right. When you use multiple star guiding, it actually works a lot better. And he got me going on doing that. And PhD2 does that, so I like that. And there's a whole lot of parameters and things you can change in PhD2 that I really like. Being able to change the aggressiveness and things of that nature. You can really improve the quality of your tracking with it. So that's kind of why I did that. But I do appreciate Brandon mentioning that to me, because that actually improved my performance quite a bit.
Yeah, he also wanted to know if it sets up PhD2 by itself, or do you have to do that separate?
You set up PhD2 when you turn this whole thing on. Okay, when you turn the Raspberry Pi on outside, okay, what I'm doing is I'm using the Raspberry Pi as a driver server. So what I do is I turn on the Raspberry Pi, and then I bring up a command window, and I start my drivers for my cameras, my telescopes in a command window. Then what I do is I start PhD2, and all I got to do in this case is just start PhD2. I don't have to do anything other than start it, because once this thing goes to it, that's when it's going to do the auto selection of all the guide stars, and it's going to do the calibration and all that stuff. But as long as it's running on the Raspberry Pi, this thing will automatically control it. And I think that is just the coolest thing. And I couldn't be happier with it. So, okay, does that answer the question?
I believe it does. Thanks.
All righty. Okay, and here's the picture again. I'm pretty happy with this. A little disappointed. I posted this on the Facebook astrophotography page. No one seemed to like it. I don't really get that. I mean, I thought this was a pretty good picture. So who knows what people like? I don't know. I thought it was pretty good, but other people weren't too thrilled about it. Maybe they've seen enough Veil Nebula pictures. Okay, I have two quick members minutes. First one is our second semi-annual Pizza Astronomy Conference. So you guys may remember a few months ago, I think last spring, I hope I'm right, we got together at Mod Pizza, and it's kind of a little experiment to see if people want to get together when it's not a meeting. And we had a good turnout, and everybody seemed to have a nice time. So a lot of people have been saying, hey, why don't we do that again? That was a lot of fun. So I'm suggesting, and it's been suggested by others, why don't we do that again? And have our second semi-annual Pizza Astronomy Conference at Mod Pizza. But the purpose of my presentation here is I'm asking for folks to send me an email, sdholland777@yahoo.com. It's down there at the bottom. Or you can just put it out on the JSCAS list server if you want. But I'd like to hear from people about when they'd like to do that, like what month would they prefer to do it in, what day of the week they'd like to do it. Because last time when we did it, there were several people who wanted to come that didn't get to come. And I just kind of like to hear from people about what nights would work with them before I, put this in motion, so that we can maximize the number of people that would like to participate in this. So just send me your ideas, and we'll put that in work, and hopefully it'll be as good as the first time we got together. Okay, last members minute, galaxy tables. Okay, so I just wanted to show this to you. You guys, I thought you guys might think this is interesting. Apparently, and I've just become aware of this recently, there are people making galaxy tables out of epoxy resin. And one of our kids, one of our sons, Joshua, actually has been making resin tables. He made a lot of cool things to take an interest in this. He's made ones that look like the ocean and a lot of different things. but he actually made one. He looked at some of our pictures on the webpage, and he made one that looks like a galaxy. And apparently this is a thing now that people are making galaxy tables out of epoxy resin. And here's an example of one. And so I just wanted to show this to you guys to let you know that there's astronomy related furniture out there now. So there you go, galaxy tables. All right, next up, David with Star Party News. Take it away, David.
David, you have a go?
All right, gonna go for the month of August. We've got a few things because our calendar has actually heated up a little bit. We had the Hack Winery event on July 9th. I've got a couple of pictures on that one, courtesy of Chris Randall. September 2nd, we've got another Hack Winery outreach event. Connie and I are going to be out of town, so I'm hoping we can get some help manning that one. September 23rd through October 1st is Okie-Tex. Doug may want to chime in and talk about that one, but I've put the website here for people who, if they're interested in going. Scuttlebutt I've heard is people to go to this one, and they do have fun. October 1st, Magnolia Creek Golf Club has asked us back, and we've got a couple of dates for them. I'll email to follow as the event gets closer, because if you don't go to the right place, you end up in the wrong place. You end up at the wrong golf course. There's going to be a 35% moon that night. It'll rise at 1 in the afternoon and transit straight up, and the event is slated to run 6 to 9, much like it did last time. Okay, October 20th through the 23rd is Fort McCavitt. These dates are confirmed, and we're trying to do here in the fall what we did last spring, is people stay through the 23rd, hang around a night, or see if you can contact El Dorado, give the website down here about possibly coming in a day early, and then hop in and go directly from the fort to El Dorado. El Dorado is going to run 24 through 29. Then we hop into later October. We are penciling out the astronomy all clubs meeting. Leonard Ferguson and I are really honed in on trying to get a day going at the George. And right now, honestly, the all clubs meeting is kind of secondary. If Aaron Clevenson and Joe Califf want to try to run with it, by all means. But Leonard's and my thing are trying to get a day going. We're going to be able to run it, but we're going to have a cap of about 500. And then we actually realized this is the first A-Day in 6 years. We haven't run an A-Day since 2016. You sit there and you work it up. 2017 was Harvey. 2018 was something else. 2019, the George closed. And then we had the pandemic. So yeah, it's been 6 years since we've actually run an A-Day at the George. November 4th, we'll have another Hack Winery outreach. Now, Hack might try to see if they can squeak one more date in October. We'll worry about that when it gets there. December 3rd, back to Magnolia Creek Golf Club. He wants us out. Be an 81% moon, but this will be after daylight savings, so we should have plenty of access to Orion Nebula and any of the planets that happen to be up. Okay, real quick, Mazatlan 2024, April 5 through 9, 2024, Eclipse land tour. Tamara Liddy, Ted Blank, and myself will be leading 3 land tours of 40 each. It is currently sold out, but if you're interested, get on the wait list, because there probably will be cancellations, and you can look this up here on the Eclipse tour site. This is our line of totality. Paul is going to be out here with a boat coming off of here, and if you're going to wonder how come the cruise side of this is so expensive, is because this ship is chartered, and that's why. So he will be able to chase the line of totality and get it away from the clouds. The land portion is going to be here, Mazatlan, away from I've just dropped the name of that city, and you see the line of totality comes pretty doggone close to Mazatlan. So we're hoping if we hop inland a mile or two, will be good. Paul does this stuff all the time, and he's really good at these eclipses. I mean, sometimes the weather doesn't play nice, but when I see these charts of cloud fraction and the percent of cloud fraction plotted over time on this particular day, Mazatlan, Torredon, Durango, the ocean location, down here around 0.3, you start working your way up Texas. The place not to be, folks, is probably Quebec. It's probably going to be clouded out. So you can kind of look at this and figure out where you might want to be. But this is the reason he's picked out Mazatlan. The only unknown we have is, drum roll, they haven't broken ground on the hotel yet we're supposed to be staying at. So that could be an oops. Okay, off the heels of Kayla, I'm sorry, with the CDC starting to relax things, where things are starting now to get back to normal. Things are kind of relaxing, but please be cautious of the BA4 and BA5 variant. I think I had BA5 about 3 weeks ago, totally asymptomatic, other than just having one of those positive tests. So just need to be wary of the health requirements and restrictions of where we happen to be having an event, whether that be HAC or the golf course, or hopefully when schools start chiming in. Okay. Hack Winery on the 9th. I didn't get a body count, but it was estimated to be a semi-full house as the sky was reasonably clear. Big kudos and thanks to Chris Randall, Bob and Leslie Eaton, and Reed Klotzer, who staffed the event. There's Leslie with her binoculars, Bob Eaton with the Mulon, Chris's monstrosity out here, and then here's Reed down here. Sounded like they had a good time for all, and we're looking forward to the next event. All right, there you go, Kayla. Top French scientist Eddie Klein tweeted a photo of a slice of chorizo and told nearly 1,000 Twitter followers that it was a space telescope image of the nearest star to the sun. Without even questioning it, tens of thousands of people believed him and started sending this viral. It came picture of Proxima Centauri, nearest star to the sun, 4.2 light years away, taken with a James Webb. This level of detail is unparalleled and is a piece of chorizo. It was just amazing that it went as viral as it did. I wouldn't be surprised if that ended up in the halls of JSC. However, he did end up in the end apologizing for this and saying, look, I just wanted to put something out, and I do apologize for this, but this is actually a piece of sausage. Don't believe everything you see on the net. This is the end point of it. Okay. How fight started in the ancient world, Ursa Major, it's a big bear. No, it's a frying pan. That's all, folks. Back to Doug.
Okay, Doug, you're on.
Okay, David, thank you very much for that presentation. You know, it's really great to see that we have so many things coming up this fall. So I encourage everybody to participate in those things. This is good. I mean, it's good that we're having local star parties. We got lots of opportunities to go out to dark sky areas this fall, and we've got people in our club that are participating in these things. So this is a good thing. I just really excited about what we're going to be doing this fall. All right, next meeting will be September 9th, and our meeting is TBD at this time. We're actually thinking about having another meeting where we have a series of short talks. I've heard that there are a couple out there. So we may have a series of short talks by our club members. So if you have anything that you would like to present at the September meeting, if it's a short talk like 10, 15 minutes or something like that, or a member's minute, please let us know. We can start planning and include that. If we discover a great main speaker that we want to use in September, we'll do that. But otherwise, we may be doing a series of short talks in September. Let us know if you got anything. So thank you very much for attending this evening, and hope you have a wonderful rest of your evening, and we'll see you in September.